Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring supernova, the colossal stellar explosions that can change the fate of entire galaxies. These events happen when stars reach a point of no return. In that final moment, gravity, heat, and pressure collide in one of the most powerful transformations in the universe. Yet a supernova is more than just a dying star. It is a forge, a signal, and a turning point in cosmic history. It can leave behind an object so dense that its matter seems impossible. It can scatter newly made elements into space, where they may later become entire worlds. And it can give astronomers a way to measure distances so vast that they reshape our understanding of the universe itself. Tonight, we'll follow these explosions from their hidden beginnings to the strange remnants they leave behind. Some discoveries may feel almost unbelievable, but each one is grounded in real science. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften. Let your breathing slow. And allow your mind to settle into stillness as we explore the science of supernova together. Let's begin. Supernova can outshine entire galaxies for a few dazzling weeks. For a short time, one dying star can become brighter than the combined light of hundreds of billions of ordinary stars. That does not mean it is larger than a galaxy. It means the explosion releases stored energy with astonishing speed, turning a single point in space into a beacon visible across cosmic distance. Astronomers have seen these sudden lights appear in galaxies so remote that the explosion happened before life on Earth became complex. For a few nights, a place that seemed empty may glow with a new star that was never really new at all. It was a death cry arriving after an immense journey through space. Then the brightness begins to fade, and the hidden work of physics becomes visible in the changing color of the light. The rise and fall tell scientists how much material was thrown outward, how hot it became, and what kind of star reached its final turning point. Every atom of iron in your blood was forged before starlight died. Inside you, there is a direct chemical link to the life of ancient stars. Iron is not something the universe made easily at the beginning. It had to be built through nuclear reactions in stellar interiors, where lighter elements were squeezed and transformed under immense heat. In massive stars, the creation of iron marks a dangerous stage because iron does not release energy in the same helpful way lighter fuels do. Once enough of it gathers in the core, the star loses one of its main supports against collapse. Long before that material ever became part of a planet, it belonged to a furnace hidden inside a star that no longer exists. Later, some of those atoms were scattered into space and folded into the cloud that made our solar system. So the metal helping your blood carry oxygen is not just biology. It is ancient astronomy, still moving through you with every breath. A supernova can create a neutron star smaller than a city. When a massive star collapses, its central region can be crushed into one of the strangest objects nature allows. The result may be a neutron star, a remnant with more mass than the sun squeezed into a sphere roughly the size of a large city. Ordinary atoms cannot survive there in their familiar form. The pressure becomes so extreme that electrons and protons are forced together, creating matter dominated by neutrons. What remains is not hot gas in the normal sense, and it is not a solid like rock or metal. It is a state of matter far beyond everyday experience. A sugar cube-sized piece would weigh more than a mountain if it could somehow be brought to Earth. Some neutron stars spin rapidly after birth, carrying the angular momentum of the original star in a smaller body. Their gravity is so intense that light itself struggles through the warped space around them. Some stellar explosions leave behind black holes instead of stars. Not every dying massive star produces a visible remnant with a surface. If the collapsing core is heavy enough, gravity may keep winning until matter falls inward beyond any known stable state. The result is a black hole, an object defined not by a surface you could touch, but by a boundary from which light cannot escape. In some cases, the explosion may still throw outer layers into space, while the center disappears behind that horizon. In others, the collapse may be so complete that the star seems to vanish with little dramatic display. Astronomers search for these outcomes by watching stars that fade away, or by studying systems where an unseen companion pulls gas from a nearby star. A black hole born this way is not an empty hole. It is concentrated gravity, the final record of a star whose core crossed a threshold that matter could not resist. Supernova helped seed Earth with the ingredients for life. The early universe was mostly made of the lightest elements. To build rocky planets, oceans, living cells, and complex chemistry, the cosmos needed stars to change that simple starting material into something richer. Supernova played a major role by spreading newly forged elements into the space between stars. Carbon, oxygen, silicon, magnesium, and many other ingredients did not stay locked inside ancient stellar interiors. Explosions hurled them outward, mixing them into great clouds of gas and dust. Later, gravity gathered parts of those enriched clouds into new stars and planetary systems. Earth formed from such recycled material, which means our world is not made from untouched cosmic leftovers. It is built from earlier generations of stars. The same process that can tear a star apart can also prepare the raw materials for soil, water, air, and biology. In that sense, life did not appear after cosmic violence by accident. It depended on it. One nearby supernova could brighten Earth's sky like a second moon. If a star exploded close enough to Earth, the event could become an unforgettable sight. It would not look like a spreading fireball across the sky. It would appear as a brilliant point of light, shining where no bright star had been before. Depending on its distance and type, it might become visible in daylight or cast faint shadows at night. Such an event would be spectacular rather than dangerous if it happened at a safe distance. The real danger would come only from a much nearer explosion, where high-energy radiation could affect the upper atmosphere. Fortunately, there are no known stars close enough to pose an obvious immediate threat. The awe comes from the possibility that the sky itself can change because of a single, distant death. Human history has recorded unexpected stellar visitors before, and each one reminded people that the heavens are not fixed. They can surprise us. The Crab Nebula began as a star recorded by ancient astronomers. In the year 1054, sky watchers in East Asia noticed a brilliant guest star in the constellation Taurus. It became bright enough to be seen during the day, then slowly faded from human view. Centuries later, telescopes revealed a strange glowing cloud in the same region. That cloud is now known as the Crab Nebula, and it is the expanding remnant of that historic explosion. At its center sits a rapidly spinning neutron star that sends out regular pulses of radiation. The nebula around it is still changing, powered from within by the energy of that compact remnant. This connection between old records and modern instruments is one of astronomy's most beautiful detective stories. A human note in an ancient sky chronicle became evidence for a physical event that scientists can still examine today. The explosion ended long ago, but its expanding remains continue to speak. Type Ia supernova helped reveal that cosmic expansion is accelerating. In the late 20th century, astronomers used a special class of stellar explosions to measure the universe on enormous scales. These events are valuable because their brightness follows patterns that can be compared from one galaxy to another. By studying how bright they appeared and how much their light had been stretched by cosmic expansion, researchers expected to trace how gravity was slowing the universe down. Instead, the data pointed to something astonishing. Distant explosions were dimmer than expected, suggesting the expansion of space had not been slowing in the simple way many models predicted. It was speeding up. This discovery led to the idea that a mysterious influence, now called dark energy, is shaping the large-scale future of the cosmos. The finding did not come from one object alone. It came from many carefully measured explosions, each acting like a marker placed deep in time. A star's death became a clue to the fate of everything. A dying star can blast its outer layers across light years. When the core of a massive star collapses, the material outside it can be driven outward with extraordinary force. Layers that once rested deep within the star begin racing into space, carrying heat, radiation, and newly exposed elements into the surrounding region. This expanding debris does not stop after a few days. It can keep moving for centuries, sweeping up nearby gas and forming a supernova remnant that spans vast distances. What began as a star with a defined edge becomes a growing structure far larger than the original object. In some remnants, filaments of glowing gas show where shock waves have compressed and heated the material. These patterns are not random decorations. They are records of motion, density, and composition. By studying them, astronomers can reconstruct the death of the star. They can see which layers were thrown fastest, which regions collided with surrounding gas, and how the explosion reshaped its neighborhood. Supernova are not endings alone, because they make new beginnings possible. A star's destruction can feel like a final act, but in space, endings often become part of a longer cycle. The material thrown outward does not simply disappear. It enters the interstellar medium, where it mixes with older gas and dust. Over time, that mixture can cool, gather, and become part of new star-forming regions. The shockwave itself may even help compress nearby clouds, pushing them toward collapse if conditioned to right. This means a single explosion can influence the birthplaces of later stars. It can also enrich those places with heavier elements that planets need. The universe is not a collection of isolated events. It is more like a continuing exchange, where one generation of stars changes the environment for the next. Supernova show that cosmic history has inheritance. They pass matter forward, not as memory in a human sense, but as chemistry, motion, and structure written into space. Massive stars explode when their cores can no longer resist gravity. For most of a massive star's life, balance keeps it alive. Gravity pulls inward, while energy from nuclear fusion pushes outward. This balance can last for millions of years, but it cannot last forever. As the star ages, it burns through different fuels in its core, moving through stages that grow hotter and more complex. Each stage is shorter than the one before it. Eventually, the inner core reaches a condition where it can no longer produce enough outward pressure to support the weight above. The collapse begins with terrifying speed. Matter falls inward, densities rise, and the star's center is transformed. What happens next depends on the mass and structure of the star, but the crisis begins with that lost balance. The same gravity that helped form the star now becomes the force that ends its stable life. A supernova is not sudden for no reason. It is the result of a long battle that gravity finally wins. White dwarfs can detonate after stealing matter from a companion star. Some supernova do not begin with a giant star collapsing. They begin in close binary systems where a white dwarf orbits another star. A white dwarf is the dense leftover core of a star that once resembled the Sun. On its own, it can remain stable for an immense length of time. Trouble begins when it pulls material from a nearby companion. As this stolen gas collects, the white dwarf grows heavier and more compressed. Under the right conditions, carbon inside it can ignite in a runaway reaction. Because the star is so dense, the burning spreads violently rather than gently. The result can be a thermonuclear explosion powerful enough to destroy the white dwarf completely. This path is different from the death of a massive star, yet it can produce one of the universe's most useful cosmic signals. A quiet remnant becomes dangerous because it lives too close to another star. A supernova shockwave can squeeze nearby gas into newborn stars. Star formation often begins inside cold clouds that are already close to collapsing under their own gravity. A passing shockwave can change the story. When material from an old explosion slams into such a cloud, it can compress parts of the gas into denser knots. If a knot becomes heavy and cool enough, gravity takes over and pulls it inward. A new star may then begin forming inside a region disturbed by a previous stellar death. Scientists think this triggering process can happen in busy stellar nurseries, where massive stars live fast and end early. Their blasts do not merely clear space. In the right setting, they can help create the next generation. This does not mean every shockwave gives birth to stars. Some are too strong and tear clouds apart instead. The outcome depends on timing, density, and environment. Space is filled with these delicate thresholds, where destruction and creation sit close together. The brightest supernova can release more energy than ordinary ones. Some stellar explosions are so luminous that they stand apart from the standard categories. These rare events can shine many times brighter than typical supernovae, making them visible from staggering distances. Their power may come from unusual engines hidden inside the blast. One possibility is a newborn magnetar, a rapidly spinning neutron star with an extreme magnetic field that pours energy into the expanding debris. Another possibility involves the explosion colliding with dense material the star threw off before it died. In that case, kinetic energy becomes light as the fast debris crashes into the surrounding shell. These brilliant events are valuable because they reveal extreme ways stars can lose mass and transform before death. They also let astronomers study distant parts of the universe that would otherwise be too faint. When one appears, it is not just brighter. It is a sign that the star lived a stranger life before it vanished. Cassiopeia. A is one of the Milky Way's youngest known remnants. This famous object lies in our own galaxy, and it gives astronomers a close view of stellar wreckage still in motion. The light from the original explosion likely reached Earth in the late 17th century, although it may have been hidden or faint to human observers. Today, telescopes see a complex expanding shell where different elements glow in different wavelengths. Oxygen, silicon, sulfur, and iron appear in distinct structures, showing how the star's inner layers were torn apart and thrown outward. The remnant is especially valuable because it is young by astronomical standards. Its debris has not yet fully blended into the surrounding medium, so the original explosion remains easier to read. Images across radio, infrared, optical, and X-ray light reveal knots, arcs, and shock fronts. Each view exposes a different piece of the story. Cassiopeia. A is not a static cloud. It is an unfolding aftermath, still teaching us how massive stars die. The first detected neutrinos from a supernova came from 1987A, when a star exploded in the Large Magellanic Cloud. Astronomers received more than light. Detectors on Earth recorded a brief burst of neutrinos, tiny particles that interact so weakly that most pass through matter unnoticed. Only a small number were caught, but they carried enormous meaning. They confirmed that a collapsing stellar core releases most of its energy in neutrinos rather than visible light. The detection also proved that particles from an explosion beyond the Milky Way could be observed directly by instruments deep underground. This was a new kind of astronomy, because it revealed the hidden collapse before the glowing display told the full story. The event became one of the most studied supernova in modern history, partly because it was close enough for detailed observation. Those few captured particles were like messengers from the center of the catastrophe. They gave scientists a glimpse into a region light could not immediately escape. Supernova neutrinos escape before the visible explosion reaches full brightness. In a collapsing massive star, neutrinos have a remarkable advantage. They can travel through dense material far more easily than light. During the earliest moments of collapse, the core becomes an incredibly crowded place where photons are trapped, scattered, and delayed. Neutrinos, however, stream outward almost at once. This means a burst of them can reach Earth before the supernova becomes visually bright. In principle, neutrino observatories could give astronomers an early warning that a massive star has begun its final transformation. That warning might arrive hours before the visible signal peaks, giving telescopes time to turn toward the right region of the sky. For a nearby event, this would be an extraordinary opportunity. Scientists could watch the explosion from its first emergence, rather than only after it had already developed. These elusive particles do not make pretty pictures, but they provide timing. They mark the moment when the star's deepest catastrophe has truly begun. Iron is the element that can doom a massive star. Fusion keeps a star alive because many nuclear reactions release energy. In a massive star, lighter elements can be fused into heavier ones through successive stages, and each stage helps support the star against gravity for a while. Iron changes the rules. It sits near a peak of nuclear stability, which means fusing it does not provide the same useful energy. Instead of acting like fuel, it becomes a dead end in the core. As iron builds up, the star loses the ability to hold itself up through ordinary fusion pressure. The core grows heavier, the inward pull strengthens, and the structure becomes unstable. This is why iron has such a dramatic role in the death of massive stars. It is not poisonous in a chemical sense. It is fatal because of nuclear physics. The element that helps humans carry oxygen can also mark the point where a star's internal engine can no longer save it. A collapsing core can rebound and help launch a stellar explosion. During the collapse of a massive star's center, matter falls inward at a tremendous rate. The core becomes so dense that it stiffens under nuclear forces, and the inward plunge can suddenly halt. This abrupt stop creates a shock wave that starts moving outward through the star. At first, the shock may struggle, losing energy as it breaks apart heavy nuclei and pushes through falling material. The explosion is not as simple as a ball bouncing. Modern models suggest that neutrino heating, turbulence, and complex flows help revive the shock and drive it farther outward. This is one reason supernova physics remains a major challenge. Scientists can observe the aftermath, but the central engine operates under conditions that are almost impossible to recreate on Earth. Still, the idea is astonishing. A star's core collapses to an extreme density. Then the violence of that collapse helps send the outer star into space. The disaster contains the mechanism of escape. Some supernova fail to explode brightly, leaving almost nothing visible behind. Astronomers have long suspected that some massive stars may die without producing a brilliant display. In these cases, the core collapses, but the expected explosion may be weak or smothered. Much of the star can fall inward, feeding a newly formed black hole, rather than being thrown into space. From far away, such an event might look like a massive star, fading or disappearing, instead of flaring into glory. This possibility matters because it could explain why certain kinds of massive stars are missing from the list of observed supernova progenitors. If the heaviest stars often collapse quietly, then the universe has a hidden death channel. Researchers search for candidates by comparing old images of nearby galaxies with new ones, looking for bright stars that are simply gone. It is a strangely haunting method. Instead of discovering a spectacular new point of light, scientists notice an absence. A star that once shone has crossed into silence. Betelgeuse will someday explode, but probably not anytime soon. Betelgeuse is one of the most famous future supernova candidates in the night sky, partly because it is close enough and large enough to make people wonder when its final moment will arrive. It sits in Orion, glowing with a reddish color that marks it as a swollen supergiant near the end of its life. A few years ago, it dimmed dramatically, which led to public excitement and wild speculation. Astronomers later found that the change was probably caused by a giant cloud of material and cooling on its surface, not an immediate countdown to explosion. The star is unstable, enormous, and already far beyond the calm middle age of a star like the Sun. Even so, stellar time does not move by human expectation. Its end could come tomorrow in cosmic terms, or many thousands of years from now. When it finally happens, the sky will gain a breathtaking new light, but patience may be required. Supernova light can take millions of years to reach Earth. When astronomers see a distant star explode, they are not watching it happen in the present moment. They are receiving light that began its journey long ago. If the host galaxy is millions of light years away, the explosion may have occurred before modern humans existed, before familiar landscapes took shape, or before life on Earth entered its current chapter. This makes every distant supernova a kind of time capsule. The flash arrives late, carrying information from a place and era we can never visit directly. Telescopes turn that delayed light into data, revealing the temperature of the debris, the speed of the blast, and the chemistry of the destroyed star. The more distant the explosion, the deeper into history we are looking. A supernova found in a faraway galaxy is not just a bright event in space. It is an ancient message, preserved by light, finally reaching our corner of the universe. Astronomers classify supernova by the fingerprints hidden in their light. A stellar explosion may look like a sudden bright point in a telescope image, but its light carries a detailed signature. When that light is split into a spectrum, dark and bright patterns appear. These patterns show which elements are present and how fast the material is moving. In this way, astronomers can tell one kind of supernova from another, even when the star itself was never seen before it died. Some spectra show hydrogen, while others do not. Some reveal silicon, helium, oxygen or iron group elements in ways that point toward a particular origin. The classification is not just naming. It is the beginning of the investigation. From those lines, researchers infer whether the explosion came from a collapsing massive star or from a white dwarf destroyed by runaway nuclear burning. The light becomes evidence. It is as if the universe leaves a coded report in every stellar death. Hydrogen lines can reveal whether a dying star kept its outer shell. One of the simplest clues in supernova astronomy comes from the presence or absence of hydrogen. Massive stars are born with hydrogen-rich outer layers, but not all of them keep those layers until the end. Strong winds, eruptions, or a nearby companion can strip the star before it explodes. When the supernova light is examined, hydrogen lines tell scientists whether that outer material was still present. If those features are strong, the dying star likely retained much of its envelope. If they are missing, the star had already been peeled down to deeper layers. That one clue changes the story of the star's life. It can reveal whether it aged alone or lived in a close relationship with another star. It can also show how much mass was lost before the final collapse. In a spectrum, hydrogen is more than an element. It is a witness to the star's last chapter. Type Ia supernova are cosmic measuring tools with remarkable consistency. Some explosions are valuable not only because they are powerful, but because they can be compared across enormous distances. Type ER supernova have patterns in how they brighten and fade that allow astronomers to estimate their true brightness. Once that is known, their apparent brightness tells us how far away they are. This is like seeing a lamp in the distance and knowing how bright it should be up close. The technique is not perfect by magic. It depends on careful calibration and corrections based on the shape of the light curve. Still, it has become one of astronomy's most important tools for mapping the universe. These explosions helped measure distances far beyond the reach of ordinary methods. They transformed stellar death into a cosmic ruler. What makes them especially powerful is the combination of visibility and predictability. A destroyed white dwarf can briefly become a measuring mark placed across deep space. Some supernova come from stars that have lost nearly all their hydrogen. A massive star can reach its final moments stripped down and exposed. If it loses its outer hydrogen envelope before collapse, the resulting explosion looks different from one produced by a star that kept its original layers. This stripping may happen through powerful stellar winds, especially in very hot, massive stars. It can also happen because of a companion star that pulls material away over time. By the end, the star may reveal helium, carbon, oxygen, or even deeper products of nuclear burning near its surface. When it explodes, the absence of hydrogen changes the spectrum and helps astronomers identify the path that led to death. These stripped explosions show that the final appearance of a supernova is shaped by the star's entire life story. Mass loss matters. Companionship matters. A star may die alone in space, yet still carry the evidence of every interaction that altered its outer skin. The Crab pulsar spins about 30 times every second. At the heart of the Crab Nebula sits a compact object that turns with breathtaking speed. It is the collapsed core left behind by the historic explosion seen in the 11th century. Each rotation sends beams of radiation sweeping through space, and when those beams cross Earth, our instruments detect a pulse. That steady rhythm is so precise that it feels almost mechanical, yet it comes from a stellar remnant only about the size of a city. The spin is a result of collapse. As the original core shrank dramatically, its rotation sped up, much like an ice skater drawing in their arms. The Crab pulsar also pours energy into the surrounding nebula, helping keep the cloud glowing long after the initial blast faded. In one object, we see a clock, an engine, and a remnant all at once. It is a lighthouse made from the crushed heart of a star. A supernova remnant can glow across radio, optical, and X-ray light. The aftermath of a stellar explosion is not visible in just one kind of light. Different parts of the remnant shine through different physical processes, and each wavelength reveals a separate layer of the story. Radio observations can trace charged particles spiraling through magnetic fields. Optical light can show cooler filaments of gas where atoms have been excited by shocks. X-rays reveal regions heated to millions of degrees, where high-speed material slams into its surroundings. A single remnant can therefore look completely different depending on the instrument used to study it. What appears faint in visible light may blaze in X-rays. What looks smooth in one band may break into knots in another. Astronomers combine these views to understand the whole structure. It is like listening to a symphony by separating the instruments, then bringing them together again. The remnant is not one glow. It is many forms of energy speaking at once. Expanding debris can race faster than any spacecraft ever built. The material thrown outward by a supernova can move at thousands of kilometers per second. That speed is so far beyond human engineering that even our fastest probe seems slow beside it. A spacecraft may take years to cross the solar system. Supernova debris can cross comparable distances with astonishing force, driven by the energy of the explosion and the violent release of pressure from the dying star. These fragments are not neat pieces like shrapnel from a machine. They are streams, knots, and sheets of gas carrying elements from different layers of the star. As they move, they crash into surrounding material and create shock fronts that heat the gas. Over time, the debris slows, but its pearly motion preserves clues about the explosion. Measuring these speeds helps astronomers estimate the energy involved and reconstruct the shape of the blast. The motion itself is a record of the star's final violence. Supernova create calcium, which later becomes part of bones and teeth. The calcium in the human body has a cosmic history that reaches far beyond Earth. This element can be made in the lives and deaths of stars, then scattered into space by explosive events. It eventually becomes part of the raw material from which planets form. On Earth, calcium entered rocks, oceans, shells, skeletons, and living cells through long chains of geology and biology. When you think of bones and teeth, it is easy to picture them as purely earthly structures. Yet the mineral strength inside them depends on atoms that had to be produced before our planet existed. Supernova are among the events that helped enrich the galaxy with such elements. They turned stellar interiors into shared material for later worlds. This makes the body strangely connected to cosmic recycling. A piece of your skeleton is not just a product of growth and nutrition. It is matter shaped by stars before it became part of life. Gold may form partly in explosive deaths and violent stellar mergers. Gold has always seemed rare and special on Earth, and its cosmic origin is just as dramatic. To create such heavy atoms, nature needs environments where atomic nuclei can rapidly capture neutrons. Neutron star mergers are now known to be powerful sites for this process, but some kinds of supernova may also contribute under the right conditions. Scientists are still studying exactly how much each source provides. What makes the question fascinating is that gold is not formed by ordinary stellar burning. It requires more extreme circumstances, where matter is flooded with particles and transformed in a rush. The atoms later spread through space and become part of new generations of stars and planets. Long after that, humans dig them from Earth's crust and turn them into symbols of value. The story behind the metal is greater than any human meaning attached to it. Its origin belongs to the most violent chemistry in the universe. Titanium, in ancient meteorites, carries memories of nearby stellar explosions. Meteorites can preserve chemical clues from the time before planets fully formed. Some contain tiny mineral grains with unusual isotopic patterns, meaning their atoms have slightly different versions of the same element than typical solar system material. Titanium is one element that can show these signatures. Such differences suggest that the cloud that formed the sun and planets was not perfectly mixed. It carried traces of material from earlier stellar events, including explosions that enriched the local region of the galaxy. By studying meteorites, scientists can examine these ancient fingerprints in the laboratory. A small stone that falls to Earth may therefore contain evidence from stars that died before the solar system existed. This is one reason meteorites are so precious scientifically. They are not just rocks from space. They are preserved archives. Their chemistry lets researchers investigate what kinds of stellar debris were present when our planetary neighborhood was still being assembled. Supernova dust can survive and drift into future planetary systems. It may seem that an explosion powerful enough to destroy a star would leave no fragile grains behind. Yet observations show that dust can form within supernova debris, and some of it may endure the harsh environment that follows. These grains can include compounds rich in carbon, oxygen, silicon, and other elements. Once they escape into interstellar space, they join the wider mixture from which new stars and planets can eventually form. Dust is more important than it sounds. It helps cool gas clouds, shields molecules from radiation, and provides surfaces where chemistry can happen. Some pre-solar grains found in meteorites appear to have formed around dying stars or in their explosive aftermath. They arrived in the early solar system already carrying unusual isotopic signatures. A grain smaller than a speck can hold a history older than Earth. Supernova dust shows how even the tiniest particles can survive immense destruction and enter new worlds. Shockwaves from dead stars sculpt glowing bubbles in interstellar gas. The space between stars is not truly empty. It contains thin gas, dust, magnetic fields, and clouds of material spread across vast distances. When a supernova shockwave moves through this environment, it can push gas outward and create expanding cavities. The edges of these cavities may glow where the gas is compressed and heated. Over long times, repeated explosions from massive stars can carve large superbubbles that reshape parts of a galaxy. These structures influence where gas collects, where it becomes too hot to collapse, and where future star formation may be encouraged or suppressed. The result is a feedback cycle between stars and their surroundings. Massive stars form from interstellar gas, then later return energy to that gas through winds and explosions. The galaxy is shaped by this give and take. A supernova does not simply happen inside a background. It alters the background, leaving enormous curved signatures in the material between stars. Some supernovae happen when two white dwarfs spiral together. In certain binary systems, both stars have already ended their ordinary lives and become white dwarfs. If they orbit close enough, they slowly lose energy through gravitational waves and draw nearer over time. The process can take millions or even billions of years, but the final stages may be dramatic. When the pair merges or transfers material unstably, the combined mass and compression can trigger runaway nuclear burning. This is one proposed route to a type ER supernova. It is difficult to observe directly because the stars are small and faint before the explosion. Afterward, the blast may erase much of the evidence. Scientists look for clues in the explosion's brightness, spectra, and surrounding environment. The idea is astonishing because it turns two stellar corpses into one final eruption. These objects are not active stars in the usual sense. Yet together, under gravity's slow pressure, they can produce a flash visible across the universe. A white dwarf explosion can completely destroy the star. Unlike some stellar deaths that leave a compact remnant behind, a thermonuclear detonation can unbind the entire white dwarf. The star is already dense, with carbon and oxygen packed under tremendous pressure. When runaway burning begins, the energy released can exceed the gravitational binding that holds the object together. Instead of leaving a core behind, the star is torn apart and dispersed into space. This is a very different fate from a massive star collapse. There is no surviving neutron star at the center, and no newly formed black hole in the usual type Ia picture. The destroyed white dwarf becomes expanding debris rich in elements created during the blast. Astronomers can study this material long after the light fades, especially in nearby remnants. The completeness of the destruction is part of what makes these events so striking. A star that once lingered as a quiet ember can end by erasing itself in a single catastrophic transformation. Core collapse supernova need stars far heavier than the Sun. The Sun will not end its life in this way because it does not have enough mass to build the kind of core that collapses violently. Stars that produce core collapse supernova begin with much greater mass. Their stronger gravity drives hotter central temperatures, which allow them to fuse heavier elements in successive stages. That path eventually leads toward a core that can no longer support itself. A smaller star follows a gentler route. It sheds outer layers and leaves a white dwarf behind. The difference begins at birth, with the amount of gas gathered into the forming star. Mass decides pressure, temperature, fuel options, lifetime, and final fate. This is one of the great organizing principles of stellar evolution. Two stars may both shine in the same sky, but their endings can be completely different. The heaviest live fast and die explosively. The lighter ones fade into remnants without tearing themselves apart. The Sun is too small to become a supernova. Our star is powerful enough to warm a planet and drive weather, oceans, and life, but by stellar standards, it is not massive enough for a violent final collapse. In the far future, it will swell into a red giant, lose its outer layers, and leave behind a white dwarf. That ending will be dramatic for the solar system, but it will not be a supernova. The core will never become hot enough to fuse elements all the way to the stage that dooms massive stars. Nor will it naturally reach the conditions needed for a runaway white dwarf explosion on its own. This distinction is reassuring and humbling at the same time. The Sun has shaped every human day, yet it belongs to a quieter class of stars. Its death will be slow compared with the sudden brilliance of a supernova. Not every star ends with a blast. Some become fading embers. Supernova can leave glowing rings around the place a star died. Before a massive star explodes, it may shed material into space through winds or unstable episodes. That material can form shells, arcs, or rings around the star. When the supernova blast finally expands outward, it may crash into these older structures and light them up. The result can be a striking pattern that reveals events from before the explosion. A glowing ring is therefore not just an aftermath. It can be a fossil record of how the star behaved while it was still alive. The shape may hint at rotation, magnetic fields, or the influence of a companion star. It may also show that the star lost mass unevenly, sending more material in some directions than others. These rings help astronomers connect the star's final blast with its earlier instability. The supernova becomes one chapter in a longer story, while the surrounding light marks pages that were written before the star died. 1987. A revealed mysterious rings around a doomed blue star. The explosion in the Large Magellanic Cloud became a landmark because astronomers could study its surroundings in unusual detail. Before the event, the star had been identified as a blue supergiant, which was surprising because many expected a red supergiant for that kind of collapse. After the explosion, images revealed a striking system of rings around the site. The central ring later brightened as the expanding blast wave reached it, producing hotspots that changed over years of observation. These structures suggested that the star had lost material before it died, possibly during an earlier phase when it looked very different. The geometry raised questions about stellar winds, rotation, and possible companion interactions. Because the event was relatively close, scientists could watch the aftermath evolve, instead of seeing only a frozen picture. It became a laboratory for how dying stars prepare their surroundings. The rings turned a famous explosion into an even deeper mystery. Ancient Chinese astronomers recorded the supernova that made the Crab Nebula. Historical sky records can preserve astronomical events with remarkable value. In the 11th century, observers noted a guest star that appeared suddenly and remained visible for many months. Their careful descriptions helped modern astronomers connect the sighting to the expanding cloud now called the Crab Nebula. This connection shows how human observation can reach across 1,000 years of scientific change. The ancient observers did not know about neutron stars, expanding remnants, or high-energy radiation. They simply documented an unusual light in the sky with enough detail to matter. Today, that record anchors the age of one of the best-studied supernova remnants. It lets scientists compare the nebula's current expansion with the known time since the explosion became visible on Earth. In a beautiful way, Mekidi astronomy and modern astrophysics became partners. A note from the past helps explain a glowing object we now study with instruments in space and on the ground. Tycho Brahe studied a supernova that challenged the unchanging heavens. In the 16th century, many scholars still inherited the old belief that the heavens beyond the moon were perfect and unalterable. Then a brilliant new star appeared in Cassiopeia. Tycho Brahe observed it carefully and showed that it did not shift position the way a nearby atmospheric or solar system object would. It had to belong to the distant celestial realm. This was a profound challenge to the idea of an unchanging sky. The event is now known as Tycho's supernova, and its remnant can still be studied today. What made Tycho's work so important was not only the brightness of the event. It was the precision of his observations and the intellectual courage to follow what the measurements showed. A sudden light in the sky helped loosen an ancient worldview. Long before photography or spectroscopy, a supernova became evidence that the universe was active, changing, and far stranger than tradition allowed. Kepler's supernova was the last clearly observed one in our galaxy. In the year 1604, a bright new star appeared in the sky and drew the attention of Johannes Kepler. It was visible to the unaided eye and became one of the great astronomical events of the early telescope age, although telescopic astronomy was only just beginning. Since then, no supernova in the Milky Way has been clearly witnessed by people on Earth in the same direct way. That long absence is surprising because astronomers estimate such explosions should happen in our galaxy every few centuries. The likely reason is that dust hides many regions of the Milky Way from visible light. An explosion on the far side of the galactic disk could be concealed from ordinary eyes. Kepler's event therefore holds a special place in history. It was not the most recent explosion in the galaxy necessarily, but it was the last one humans plainly saw. The next could be hidden or unforgettable. Modern telescopes find thousands of supernovae in distant galaxies each year. For most of history, supernova discoverers depended on patient observers noticing a new point of light. Now the search is systematic. Robotic surveys scan large areas of sky, compare new images with older ones, and flag objects that have changed. This approach has transformed supernova astronomy from rare discovery into statistical science. By finding thousands of events, researchers can study patterns across many kinds of galaxies and stellar environments. They can catch unusual explosions, measure cosmic distances, and improve models of how stars die. Large samples also reveal rare categories that might have been missed in the past. A single strange event can be interesting, but thousands allow scientists to ask deeper questions. Which galaxies produce which types? How often do the brightest events occur? What kinds of stars are responsible? The night sky is no longer just watched. It is monitored with extraordinary persistence, allowing stellar deaths to be found almost as soon as they announce themselves. Automated sky surveys now catch stellar explosions while they are still rising. Timing is everything when a star explodes. The earliest light can carry clues that vanish quickly as the debris expands and cools. Automated surveys make it possible to detect a supernova before it reaches peak brightness, sometimes within hours or days of first light. This early discovery lets astronomers trigger follow-up observations across many wavelengths. They can watch the temperature change, look for signs of material surrounding the star, and search for brief flashes caused by shock breakout or companion interaction. These opening moments are precious because they connect the visible event to the star's final structure. Older astronomy often found supernova after they were already well developed. Modern surveys are changing that by turning the sky into a continuous experiment. The first rise of light is like the opening page of a mystery. If captured early, it can reveal details that later chapters blur or erase. Some stars shed shells of gas before their final explosion. The last stages of a massive star's life can be unstable. Long before the final collapse, the star may push material into space through powerful winds or sudden outbursts. These shells can sit around the star like evidence of earlier distress. When the eventual explosion reaches them, the collision can produce extra brightness and distinctive spectral features. This tells astronomers that the star was not calm before death. It may have been losing mass rapidly, pulsing, or responding to changes deep in its interior. In some cases, the material seems to have been ejected only years or decades before the supernova, which is remarkably recent in stellar terms. That timing raises major questions about how stars behave at the end. Do internal burning stages disturb the surface? Do companions help pull material away? These shells turn the surrounding space into a diary. The explosion illuminates what the star had already thrown off. A supernova blast can collide with old stellar winds. Massive stars often shape their surroundings before they die. During their lives, they can blow steady streams of particles into space, creating bubbles and layered regions around themselves. When the final blast races outward, it does not expand into untouched emptiness. It may run straight into material created by the star's own earlier wind. This collision can heat gas, strengthen shocks, and produce radiation that reveals the density of the environment. In some remnants, the interaction with old winds helps explain bright arcs or uneven structures. The details depend on what kind of wind the star had during different phases of its life. A red supergiant wind is dense and slow. A hotter star can drive a faster, thinner wind. These earlier outflows build the stage on which the supernova later performs. By studying the collision, astronomers can infer not only how the star died, but how it lived before the final moment. That collision can make the explosion glow far longer than expected. Some supernovas stay bright because their expanding debris keeps crashing into nearby material. The explosion begins with a powerful release, but the ongoing interaction converts motion into light over an extended period. If the surrounding gas is dense, this process can maintain luminosity for months or even years. Astronomers recognize such cases through narrow emission lines and unusual light curves that do not fade as quickly as simpler models predict. The extra glow reveals that the star had placed material around itself before it died. In effect, the supernova runs into its own past. The brightness becomes a record of that encounter. These long-lasting events are especially useful because they make hidden mass loss visible. Without the collision, the old gas might have remained too faint to study. With it, the star's previous eruptions or winds are exposed by the blast. the lingering light is not just aftermath. It is an interaction still unfolding. Supernova remnants can accelerate cosmic rays to astonishing energies. Cosmic rays are high-speed particles that travel through space and sometimes strike Earth's atmosphere. For decades, scientists have suspected that supernova remnants are major sources of these particles. The reason lies in shock waves. As the expanding blast moves through magnetized gas, charged particles can bounce back and forth across the shock, gaining energy with each crossing. Over time, some are accelerated to speeds close to that of light. This process helps explain why remnants glow in radio waves and high-energy gamma rays. It also connects stellar explosions to particle physics on a galactic scale. The remnant becomes a natural accelerator, far larger than anything humans can build. Instead of using laboratory magnets in a tunnel, the universe uses expanding shock fronts across light years. Each particle that escapes carries a trace of that violent training. Supernova remnants therefore do more than mark where stars died. They help fill the galaxy with fast-moving fragments of atomic matter. Cosmic rays from ancient explosions may still pass through you. Every moment, high-energy particles from space arrive at Earth. Most collide with molecules high in the atmosphere, creating showers of secondary particles that can reach the ground. Some of the original cosmic rays may have been accelerated in supernova remnants long before human history began. By the time their effects reach us, their exact birthplace is usually difficult to identify because magnetic fields bend their paths. Still, their existence means stellar explosions are not only distant spectacles. They can produce particles that become part of Earth's constant radiation environment. The amounts at ground level are usually harmless, and life has evolved beneath this steady background. Yet the thought is astonishing. A particle set in motion by an old stellar blast may cross the galaxy, strike our atmosphere, and briefly become part of the invisible weather around us. Supernova are not confined to telescope images. In a subtle way, their echoes can arrive at your body. Nearby supernova may have sprinkled radioactive iron onto Earth's seafloor. Deep beneath the ocean, scientists have found traces of iron-60 in ancient crusts and sediments. This isotope is rare on Earth because it decays away over geological time, so finding it in relatively recent layers suggests it arrived from space. One powerful explanation is that one or more stellar explosions happened near our solar system a few million years ago. The debris did not arrive as a blazing storm that burned the planet. It likely drifted in as fine dust, carried through interstellar space, and eventually settling into Earth's environment. That means the seafloor may hold physical evidence of events that happened beyond the solar system. The idea is extraordinary because it connects deep ocean geology with dying stars. A sample lifted from Earth's crust can become a message from a nearby stellar catastrophe. The ocean floor, usually thought of as earthly and slow, may contain ashes from a star that died close enough to touch our planet chemically. A supernova shock can compress magnetic fields into tangled glowing arcs. When an expanding blast wave moves through space, it does not only sweep up gas. It also disturbs magnetic fields that thread through the interstellar medium. These fields are invisible on their own, yet they influence charged particles and shape how energy moves through the remnant. As the shock advances, it can squeeze and amplify magnetic fields, creating regions where particles spiral and radiate. The result can be bright arcs, rims, and filaments that reveal the hidden structure of magnetism in space. These features are not decorative. They show where the blast is strongest, where particles are being energized, and where the surrounding environment resists the expansion. In some remnants, thin, bright edges suggest extremely efficient particle acceleration. The physics is complex, but the picture is simple enough to feel astonishing. A dead star can take an invisible galactic field and make it visible through motion, heat, and light. The Veil Nebula is a vast remnant of an ancient explosion. In the constellation Cygnus, delicate strands of glowing gas mark the remains of a star that exploded thousands of years ago. Through a telescope, the structure looks like wisps stretched across the sky, but those filaments are enormous shock fronts moving through interstellar material. The original star vanished long before recorded history, yet its expanding remains still cover a region far wider than the full moon appears from Earth. The visible threads shine because the blast wave is heating gas and exciting atoms as it passes. Different colors reveal different elements and temperatures, which lets astronomers study the impact of the explosion on its surroundings. What makes this object especially compelling is its scale. A single star died, and the aftermath became a sprawling celestial structure large enough to span many light years. The Veil Nebula shows that a supernova does not end with a flash. It can leave a luminous architecture that endures for millennia. Supernova can carve giant cavities through the gas between stars. Galaxies are filled with gas that can be gathered, heated, pushed aside, or blown open. When massive stars explode, their shockwaves drive energy into this material and can clear out huge low-density regions. In places where many massive stars are born together, repeated explosions can overlap and create superbubbles. These cavities may stretch across hundreds of light-years, with hot gas inside and denser material swept toward their edges. This sculpting changes the future of the region. Gas that is dispersed may stop forming stars for a while. Gas piled along a shell may later become dense enough to collapse. In that way, supernovae help regulate the rhythm of star birth inside galaxies. They are part of a feedback loop between stars and the medium that forms them. The galaxy is not still between one generation and the next. It is being stirred, hollowed, and reshaped by the deaths of its brightest stars. Stellar explosions help stir galaxies like enormous cosmic mixing spoons. Elements made in stars would not matter as much if they stayed locked in one place. Supernova help spread them. Their blasts drive enriched material outward, pushing atoms from stellar interiors into wider galactic space. Over time, this mixing changes the chemistry of the gas from which later stars form. A young star born after many earlier explosions can contain more heavy elements than one born near the beginning of cosmic history. This process is one reason galaxies develop chemical histories. Different regions may be enriched at different rates, depending on how many stars have lived and died there. Supernova also drive turbulence, which blends gas and influences how clouds fragment. The result is a galaxy that slowly becomes more complex. Every generation leaves a chemical inheritance for the next. Without this mixing, the building blocks of rocky planets and biological chemistry would remain far more unevenly distributed. Stellar death helps make galaxies fertile. Without supernova, galaxies would have far fewer heavy elements. The universe began with mostly hydrogen, helium, and a little lithium. That simple chemistry could make stars, but not rocky worlds like Earth in any familiar form. Heavy elements had to be manufactured later, inside stars and during violent stellar events. Supernova are among the main ways those elements escape into space. They enrich galaxies with oxygen, silicon, sulfur, iron, and many other ingredients needed for planets and life. If these explosions never happened, much of that material would remain trapped in stellar remnants or would never be made in sufficient amounts. Galaxies would still shine, but their later generations of stars and planets would be very different. There would be fewer solid surfaces, fewer mineral-rich worlds, and less chemical variety. Supernova are therefore not just dramatic endings. They are one of the reasons the universe became materially interesting. The complexity beneath your feet is tied to explosions that scattered the periodic table into space. The universe's first supernova may have enriched space with new chemistry. The earliest stars formed from gas, almost untouched by previous generations. They were born in a universe without the rich mix of elements we see today. When some of those first stars died, their explosions changed the chemical future of everything around them. They released heavier elements into the surrounding gas, creating the first seeds of cosmic complexity. Later stars formed from material that was no longer pristine. Even a tiny amount of enrichment could change how gas cooled, how clouds fragmented, and what kinds of stars formed next. This transition marks one of the great turning points in cosmic history. The first explosions helped move the universe from simplicity toward diversity. They were not only bright events in a young cosmos, they were chemical awakenings. Before them, space lacked the ingredients for rocky planets. After them, the possibility of worlds like ours began to enter the story. The earliest stars likely exploded very differently from stars today. The first stars formed from material with almost no heavy elements, and that changed how they lived. Without those elements, gas cooled less efficiently, which may have allowed some early stars to grow extremely massive. Their interiors, winds, and final deaths may have differed from the stellar explosions astronomers commonly see nearby. Some may have collapsed into black holes. Others may have erupted through processes that are rare or absent among modern stars. Because these events happened so long ago, direct evidence is difficult to gather. Scientists search for their traces in ancient stars, distant galaxies, and chemical patterns that seem to preserve early enrichment. The idea is powerful because it reminds us that supernovae are not all timelessly the same. They depend on the conditions of the era in which stars are born. The universe had a childhood, and the deaths of its first stars may have been stranger than almost anything happening today. Parent stability supernova can tear enormous stars completely apart. In the most massive stars, light itself can help trigger catastrophe. Deep inside an extremely hot core, energetic photons may transform into pairs of particles and antiparticles. This process removes pressure that was helping support the star. Once pressure drops, the core contracts, temperatures surge, and explosive oxygen burning can begin. If the star is in the right mass range, the energy release can be so overwhelming that nothing compact remains. The entire star is blown apart. This is different from a normal core collapse, where a neutron star or black hole may be left behind. A parent stability event can erase the star completely and throw enormous amounts of heavy elements into space. Astronomers study this possibility partly because it may explain some unusually bright explosions and the chemical signatures of early cosmic history. The physics sounds almost unbelievable. Light becomes matter, pressure vanishes, and a star destroys itself so thoroughly that no central remnant survives. Some supernovae are powered by radioactive nickel made during the blast. After the initial explosion, the glow does not simply continue on stored heat alone. In many cases, newly created radioactive nickel plays a central role. The blast forges nickel-56, which decays into cobalt and then into iron. Each step releases energy that heats the expanding debris from within. This internal heating helps shape the light curve, which is the record of how the supernova brightens and fades over time. By studying that fading, astronomers can estimate how much nickel was made. This gives them a way to probe the violence and temperature of the explosion. A larger amount of nickel often means a brighter event, although other factors also matter. The idea is fascinating because the supernova becomes a glowing clock, powered by nuclear transformation. Long after the first shock has raced outward, unstable atoms inside the debris continue to feed the light. The fading star is illuminated by its own freshly made radioactivity. Radioactive decay can keep a supernova glowing after the explosion fades. A supernova's brightness changes in stages. The first flash may come from the initial release of energy and the heating of the outer layers. Later, as the debris expands and cools, radioactive decay can become the main source of continuing light. This is why some supernovae fade in a smooth pattern that reflects the decay of particular isotopes. The expanding material becomes a vast, thinning cloud with energy deposited from within by unstable nuclei. Photons slowly escape, carrying information about the composition and structure of the debris. For astronomers, the fading is not a disappointment. It is a measurement. The rate of decline can reveal which elements are present and how effectively their energy is trapped. A supernova, therefore, does not just shine because it exploded. It shines because its ashes are still changing. The light we see weeks or months later may be powered by atoms transforming into more stable forms. A supernova light curve reveals how the blast changes over time. Astronomers do not only measure how bright an explosion is at one moment. They follow its brightness night after night, creating a curve that records the event's rise, peak, and decline. That shape contains a surprising amount of information. A fast rise may suggest a compact star or a thin outer layer. A slow decline may point to radioactive heating or interaction with surrounding gas. A plateau can reveal stored energy leaking from a hydrogen-rich envelope. By comparing light curves, scientists can identify different families of explosions and test models of stellar death. The curve is like a biography written in brightness. It shows how heat moves through the debris, how energy escapes, and how the expanding material changes as it thins. Two supernovae may look similar at discovery, yet their later fading can reveal completely different origins. Time turns the flash into a story, and careful observation reads it. Spectra let astronomers read the chemical ashes of a dead star. When light from an explosion is spread into its colors, it becomes a chemical record. Every element absorbs or emits light at particular wavelengths, but the fast expansion of the debris shifts and broadens those features. To an expert, those smeared lines reveal both composition and motion. Oxygen may point to material from a massive star's interior. Silicon can be important in identifying a thermonuclear white dwarf explosion. Helium, calcium, and iron group elements each add clues to the case. Spectra also change with time as the outer layers become transparent and deeper material is exposed. This means astronomers can watch different parts of the explosion come into view. The process is almost like peeling back the star after death, not with a knife, but with light. A spectrum turns a distant point into a physical object. It allows scientists to ask what the star was made of and how those materials were launched outward. A neutron star can receive a kick during an uneven explosion. When a massive star dies, the blast is rarely perfectly balanced. More material may be ejected in one direction than another, and neutrino emission may also vary across the collapsing core. That imbalance can push the newly formed neutron star away from the explosion site. Some of these compact remnants travel through space at hundreds of kilometers per second. This kick is important because it helps explain why pulsars are often found offset from the centers of their remnants, or racing through the galaxy on unusual paths. The effect is a reminder that a supernova is not a tidy sphere expanding evenly in all directions. It is a turbulent, three-dimensional event filled with instabilities. A tiny asymmetry in such a powerful explosion can have enormous consequences. the star's crushed core becomes a runaway object, carrying the imprint of the blast that made it. Its motion is the recoil of stellar death. Some neutron stars flee their birthplaces at tremendous speeds. A neutron star may begin life near the center of a supernova remnant, but it does not always stay there. If the explosion gave it a strong enough kick, it can shoot away like a compact stellar cannonball. Over thousands of years, it may move far from the glowing debris that marks the original blast. Some leave trails or bow shocks as they plow through surrounding gas. Others are found isolated, with their birthplace difficult to reconstruct. Their speed tells scientists about the asymmetry of the explosion and the violent conditions of core collapse. It also affects the future of binary systems. If a massive star had a companion, a strong kick can disrupt the pair and send both objects on new paths. These runaway remnants turn supernova into engines of motion. A star dies, and its collapsed core may spend the rest of its existence crossing the galaxy at astonishing speed. Pulsars are spinning neutron stars that sweep beams through space. A pulsar is not flashing on and off like a lamp. It is rotating. Its beams of radiation sweep outward from magnetic regions, and if Earth lies in the path, we detect regular pulses. This lighthouse effect can be incredibly precise, with some pulsars keeping time better than many human-made clocks. Their signals reveal rotation rates, magnetic fields, and gradual energy loss. Young pulsars are often connected to supernova remnants, which tells astronomers they were born in stellar explosions. Over time, the spin slows as energy is carried away. Some pulsars rotate many times per second, while others are slower. Their regularity has made them useful for testing physics, detecting extreme environments, and even imagining maps for interstellar navigation. What makes them so captivating is their contrast. They are small, dense, and dark by ordinary standards, yet they can announce themselves across thousands of light years with a rhythm born from collapse. Magnetars may be born in especially intense stellar explosions. Among neutron stars, magnetars are the extreme members of the family. They possess magnetic fields so powerful that they reshape the behavior of matter and radiation around them. Scientists think some are created when a collapsing core rotates rapidly and amplifies magnetic fields during the birth of the neutron star. This may happen in unusual supernova, where the central engine is especially energetic. Magnetars can produce sudden outbursts and giant flares, releasing huge amounts of energy from magnetic stresses in their crusts and magnetospheres. Their existence shows that a supernova does not create only one kind of compact remnant. The conditions during collapse matter deeply. Rotation, magnetic field growth, and internal turbulence can decide whether the newborn object becomes an ordinary pulsar or something far more intense. A magnetar is like a reminder that gravity is not the only force that can become extreme after a star dies. Magnetism can become almost unimaginable too. A magnetar's magnetic field can outshine ordinary physics in strange ways. Near a magnetar, the magnetic field is so intense that familiar intuition begins to fail. It can affect how atoms behave, how radiation travels, and how the surrounding plasma moves. The field may be trillions of times stronger than the strongest magnets found in everyday technology. Energy stored in that field can be released in sudden bursts when the star's crust shifts or magnetic structures rearrange. These outbursts can be detected across great distances. Some are brief flashes, while rare giant flares can momentarily become among the brightest high-energy events in the galaxy. The star itself is not large, yet the magnetic energy around it is staggering. Magnetars make the aftermath of supernova feel even more extraordinary because they show what can remain after collapse. Not just dense matter, not just fast rotation. A newborn remnant can also carry a magnetic field so powerful that space around it becomes an active, violent environment. Superluminous supernova may be powered by newborn magnetars. Some stellar explosions are too bright to be easily explained by the usual radioactive heating alone. One leading idea is that a rapidly spinning magnetar forms at the center and injects extra energy into the expanding debris. As the magnetar slows, it loses rotational energy, which can heat the material around it and make the supernova shine far more intensely. This model can explain why certain events remain luminous for longer than expected, and why their light curves have unusual shapes. The concept is dramatic because the explosion is not powered only by the initial blast. A compact engine continues working inside the debris, feeding it from within. Astronomers compare observations with models to infer the magnetar's possible spin and magnetic strength. These events may reveal what happens when a star's death produces a remnant born with extraordinary properties. In that case, the brightest display is partly driven by the tiny object hidden at its center. Some exploding stars were once hidden inside thick cocoons of dust. Not every dying star is easy to see before or during its explosion. Some are surrounded by dust created through winds, eruptions, or mass loss in their final stages. Dust absorbs visible light and re-radiates energy in infrared wavelengths, which can make the star faint or invisible to ordinary optical surveys. When the explosion happens, the blast and radiation may heat or destroy some of this dust, revealing a complex environment that had been concealed. Infrared observations are especially important for finding and understanding these hidden events. They show that our census of supernova can be biased toward explosions that are not heavily obscured. This matters in dusty galaxies, where star formation is intense and many massive stars may die behind curtains of material. A hidden supernova is still powerful, but its light reaches us transformed. The dust changes what we can see, and in doing so, it tells us how the star prepared for death. Infrared telescopes can uncover supernova that visible light partly misses. Dust is one of astronomy's great filters. It can block and scatter visible light, making distant events harder to detect. Infrared light passes through dust more effectively, which allows telescopes working at those wavelengths to reveal explosions that optical surveys may overlook. This is especially useful in crowded star-forming regions and in galaxies rich with dust. Infrared observations can also measure warm dust created or heated by the explosion. That gives scientists insight into the environment around the dying star and the material it lost before the blast. Some supernova look modest in visible light, but become far more revealing in infrared data. This changes the way astronomers estimate how often stars explode and where those explosions occur. The universe does not present every event in the same color. To understand stellar death fully, researchers need more than human visible light. Infrared telescopes open a deeper view into obscured cosmic endings. Light echoes can reveal explosions that happened centuries ago. A supernova's light does not always reach us by one direct path. Some of it can travel outward, strike dust clouds, scatter, and arrive at Earth long after the original flash faded. This delayed signal is called a light echo. It can appear as a faint, moving glow around the site of an old explosion. The idea is remarkable because it lets astronomers study light from an event that humans missed, or only partly recorded. In some cases, spectra of light echoes can reveal the type of a centuries-old supernova. The dust acts like a natural mirror, preserving a delayed glimpse of the blast. It also provides three-dimensional information about dust around the remnant. A light echo turns space itself into an archive. The original star is gone, the bright event is over, and yet its light can still be found taking longer routes through the surrounding darkness. Interstellar dust can reflect supernova light like a delayed memory. Dust grains between stars are tiny, but across huge clouds they can redirect enough light to matter. When a supernova flash reaches such a cloud, some photons scatter toward Earth after traveling an indirect path. Because that path is longer, the reflected light arrives later. The effect can make the past visible again, not as imagination, but as actual delayed radiation from the event. Astronomers can use this to study both the explosion and the dust. The shape and motion of the echo reveal where the dust lies in 3 dimensions. The color of the scattered light can show how the grains affect different wavelengths. This is a beautiful example of how empty-looking space contains useful structure. Dust is usually treated as something that hides the universe. Here, it becomes a witness. It catches the outgoing flash, holds its direction for a while, and sends a faint portion onward after the main event has vanished. Webb has seen delicate dust structures near Cassiopeia A. The James Webb Space Telescope has brought a new infrared view to one of the galaxy's most studied remnants. In that view, worn dust and fine structures appear with remarkable detail, revealing features that were difficult to see before. Cassiopeia A is valuable because it is young, nearby by galactic standards, and rich with material from a massive star's interior. Webb's infrared sensitivity helps astronomers examine dust formation, shock interaction, and the distribution of elements in the expanding debris. One especially intriguing feature has been nicknamed the Green Monster because of how it appears in processed images. Its origin is still being studied, and it may trace material shaped by the blast wave and surrounding gas. These observations matter because dust from stellar explosions may contribute to the raw material of future stars and planets. Webb is not just taking pretty pictures. It is helping scientists understand how destruction produces grains that can survive into cosmic recycling. Chandra detects X-rays from supernova remnants heated to extreme temperatures. The Chandra X-ray Observatory studies some of the hottest and most energetic regions in supernova remnants. When fast-moving debris collides with surrounding gas, shockwaves can heat material to millions of degrees. At those temperatures, the gas emits X-rays, which cannot be studied well from the ground because Earth's atmosphere blocks them. Chandra's observations reveal where the most energetic collisions are happening and which elements are present in hot plasma. In remnants like Cassiopeia A and Tycho's remnant, X-ray images show knots, shells, and regions rich in silicon, sulfur, calcium, or iron. These data help astronomers map the explosion's inner layers after they have been thrown outward. X-rays also show where particles may be accelerated to very high energies. Without this view, much of the remnant's most violent physics would remain hidden. Chandra let scientists see the aftershock of stellar death in a form of light our eyes could never detect. Hubble has watched debris from 1987 at changing for decades. Few supernovae have been followed as closely over time. Because 1987A occurred in a nearby companion galaxy to the Milky Way, the Hubble Space Telescope has been able to monitor its aftermath with extraordinary patience. Year by year, the expanding material has interacted with surrounding rings and gas lost by the star before it exploded. Bright spots have appeared, changed, and faded as the blast wave struck denser regions. This long record is scientifically precious because most astronomical events evolve too slowly for human lifetimes. Here, researchers can actually watch the remnant develop. Images across decades show that a supernova is not a single moment frozen in history. It is an ongoing process with changing structure, temperature, and illumination. The data help scientists test predictions about shockwaves and circumstellar material. Hubble's view has turned one stellar death into a continuing story that humans have been able to follow almost in real time. A supernova can briefly flood space with invisible neutrinos. During the collapse of a massive star's core, an enormous number of neutrinos are produced. They stream outward in a burst that carries away most of the gravitational energy released by the collapse. To human senses, this flood would be completely invisible. Neutrinos have no electric charge and interact only weakly with matter, so almost all of them pass through the star, surrounding space, planets, and people without leaving a trace. Yet their importance is enormous. They are central to the physics of core collapse, and they may help transfer energy that allows the explosion to succeed. For detectors on Earth, catching even a handful from a nearby event would be a major scientific treasure. The contrast is almost hard to grasp. A supernova can release a storm of particles so vast that numbers lose meaning, while our instruments notice only the rare few that happen to interact. Invisible does not mean insignificant. Neutrinos from collapsing stars pass through planets almost without stopping. Matter is mostly transparent to neutrinos. A particle born in a stellar collapse can cross enormous distances and then pass through Earth as if our planet were barely there. This strange ability comes from the way neutrinos interact through the weak nuclear force, which makes collisions with ordinary atoms extremely unlikely. To detect them, scientists build huge instruments filled with water, ice, or other materials, then watch for the rare flashes created when one finally interacts. The vast majority pass through unnoticed. This makes neutrinos frustrating and wonderful at the same time. They are difficult to catch, but they carry information from places light cannot easily escape. In a supernova, they emerge from deep inside the collapsing core, long before photons can travel freely through the dense stellar material. When a detector records them, it is capturing a signal from the hidden center of the event. A nearly ghost-like particle becomes a direct messenger. Supernova neutrino detectors wait patiently in deep underground laboratories. Around the world, enormous detectors are built beneath rock, ice, or other shielding to reduce interference from ordinary background radiation. They are not watching the sky in the familiar way. They are waiting for rare particle interactions caused by neutrinos passing through their detector material. Most days, they record signals from the sun, the atmosphere, or other sources. But if a nearby massive star collapses, the instruments could register a sudden burst from the same direction in time. Networks can share alerts so astronomers know to search for the coming light. This patient readiness is one of modern astronomy's most exciting forms of preparation. A detector may wait years or decades for a galactic supernova, yet the payoff would be extraordinary. It would reveal the hidden timing of the collapse and give telescopes an early chance to observe the visible explosion. These laboratories are like listening posts for a stellar alarm that may sound without warning. Gravitational waves may someday reveal hidden details of stellar collapse. When a massive star's core collapses unevenly, it can disturb space-time itself. Those ripples are gravitational waves. If a supernova happens close enough and with enough asymmetry, future detections could provide information that light and neutrinos cannot fully supply. The waves would come from the motion of dense matter deep in the core, where the explosion mechanism is born. That region is hidden from ordinary telescopes. Gravitational waves could reveal rotation, turbulence, and oscillations during the first moments of collapse. Detecting them from a supernova is difficult because the signal may be weak and complex. Still, the possibility is thrilling. It would add a new sense to astronomy. Light shows the glowing debris. Neutrinos reveal particle escape from the core. Gravitational waves would carry the pattern of the collapsing mass itself. Together, those signals could turn a future nearby supernova into one of the richest scientific events ever observed. The core of a massive star can collapse in less than a second. For millions of years, a massive star may shine with a balance that seems steady from the outside. Then, in its deepest center, that balance can fail with almost unimaginable speed. Once the core loses support, gravity takes over so violently that the central region falls inward, faster than any ordinary material process we experience on Earth. In less time than it takes to blink, the heart of the star can be crushed from something planet-sized into a compact object only kilometers across. The outer star does not immediately understand what has happened. The catastrophe begins hidden, buried under layers of gas that are still shining as though the star is alive. This is one of the most astonishing contrasts in astronomy. A star may look calm from far away, while its center is already undergoing a transformation beyond ordinary matter. The explosion we later see begins with that secret inward plunge. Outer layers may take longer to learn the core has died. A star is enormous, and even a disaster at its center cannot communicate instantly through all its layers. When the core collapses, the outer regions are still far away in physical terms, separated by vast depths of hot gas. Information about the collapse moves outward through shocks, pressure changes, and radiation. Until those signals arrive, the surface may continue shining much as it did before. This creates a strange delay between the star's hidden death and the visible event. The core has already crossed its final threshold, yet the outer layers have not begun their dramatic departure. When the shock reaches them, the star changes from a stable object into an explosion that can be seen across galaxies. That delay makes the event feel even more dramatic. The star dies from the inside out. Its surface is the last part to discover the truth. By the time the light announces the event, the deepest ending has already happened. A dying star's final moments can depend on turbulence deep inside. The last seconds of a massive star are not smooth or simple. Inside the collapsing region, matter churns, falls, rebounds, and swirls in patterns that are extremely difficult to model. Turbulence can help determine whether the outward shock gathers enough strength to escape or stalls under the weight of infilling material. Small differences in motion can grow into large differences in outcome. A star with similar mass to another may produce a stronger explosion, a weaker one, or even collapse with very little light. This makes supernova science both challenging and fascinating. The visible blast depends on hidden fluid motions in a place no telescope can directly see. Scientists use supercomputer simulations to follow these chaotic flows, but the problem remains one of the great puzzles of astrophysics. In the final moments, the star is not just falling inward. It is boiling with violent internal weather, and that motion can shape the fate of everything that follows. Shells of silicon and oxygen can mix before the blast. Late in the life of a massive star, its interior becomes layered by nuclear history. Different shells contain different fuels and ashes, arranged by temperature, density, and depth. Silicon may burn closer to the center, while oxygen lies in a neighboring layer. Yet the star is not always neatly divided. During the final phases, instabilities can stir the interior and mix material across boundaries. That mixing can affect how the collapse begins and how the explosion moves outward. It can also influence the chemical pattern seen later in the debris. When astronomers study a remnant and find elements distributed in surprising ways, they are often seeing the result of motion that happened before or during the explosion. The star's inner structure was not a stack of perfect shells waiting passively for death. It was active, changing, and unstable. Before the blast became visible, the star had already begun rearranging its deepest ingredients. Supernova explosions are often lopsided rather than perfectly round. It is natural to imagine an exploding star as a smooth sphere expanding evenly into space. Real supernova are usually messier and more interesting. The core collapse can be asymmetric, the surrounding material can be uneven, and the explosion may push harder in some directions than others. Later observations of remnants often show clumps, jets, arcs, and irregular shapes rather than perfect shells. This matters because asymmetry changes the distribution of elements and the motion of any compact object left behind. It also affects how bright the event looks from different directions. A supernova viewed along one axis may not appear exactly like the same event viewed from another. The lopsidedness is not a flaw in the picture. It is part of the physics. Stars rotate, convect, lose mass, interact with companions, and die in complex environments. Their explosions carry that complexity outward. The universe rarely chooses perfect symmetry when turbulence is available. Asymmetry can decide whether a neutron star is flung away. When a supernova is uneven, the newly formed compact remnant may receive a powerful push. This happens because momentum has to balance. If more material is thrown in one direction, or if energy escapes unevenly, the neutron star can recoil in another direction. The effect can turn a newborn remnant into a fast-moving object, but leaves the center of its own debris field. Over time, the offset becomes visible, allowing astronomers to connect motion with the violence of birth. The same principle is familiar in a simple way when a released balloon darts backward as air rushes out. But the scale here is cosmic. A crushed stellar core, heavier than the Sun, can be launched across space by the imbalance of an explosion. This makes the shape of the blast more than a visual detail. It can determine the future path of one of the densest objects in the universe. Some remnants show jets that hint at powerful internal motions. In certain supernova remnants, material appears extended along preferred directions, as though the explosion had channels or outflows. These jet-like features can suggest that the blast was shaped by rotation, magnetic fields, or uneven flows deep in the collapsing star. They do not always mean a clean beam like those from some black holes. Often they are messy structures made of knots of debris rich in particular elements. Their existence tells scientists that the explosion was not purely spherical. Something inside gave certain regions extra speed or directed motion. By measuring composition and velocity, astronomers can ask whether the jets came from the star's inner layers or from later interaction with surrounding gas. The answer helps reveal the hidden engine of the blast. A remnant is not only a cloud. It is a three-dimensional record. If jets are present, they point back toward forces that acted during the first seconds of stellar death. Cassiopeia. A contains clumps moving faster than the main blast wave. Inside this young remnant, astronomers have identified knots of material that appear to move at remarkable speeds. Some of these clumps are rich in elements forged deep inside the original star. Their motion suggests that the explosion launched pieces of inner material outward in a highly uneven way. Instead of the simple shell where all debris moves together, the remnant contains fast fragments, slower gas, shock-heated regions, and structures shaped by the surrounding environment. This complexity makes Cassiopeia a superb laboratory for understanding how massive stars actually break apart. The fastest knots are especially valuable because they may preserve information from the earliest stages of the blast. They are like thrown sparks from the star's buried interior, now racing through a much larger field of debris. By tracking them over time, scientists can reconstruct the geometry of the explosion. The remnant becomes a moving map of violence, not a frozen picture. Supernova debris can reveal which layers once lived inside the star. A massive star builds elements in stages, and those stages leave a layered interior before collapse. After the explosion, those layers are torn apart and thrown into space. By studying where different elements appear in a remnant, astronomers can infer what came from the star's outer regions and what came from deeper inside. Oxygen, neon, magnesium, silicon, sulfur, calcium, and iron can each tell part of the story. Their locations and speeds show how thoroughly the explosion mixed the star. Sometimes deeper material is found far outward, which means the blast overturned the original structure. In other cases, certain elements remain concentrated in particular zones. This is one of the most direct ways to study a star after it has vanished. The original object is gone, but its internal anatomy has been scattered into view. A supernova remnant is not just wreckage. It is a dismantled star with its hidden layers exposed across space. Oxygen-rich remnants point to massive stars that built heavy elements. Some supernova remnants show unusually strong signs of oxygen and other elements made in massive stellar interiors. These objects are important because they connect observed debris with the nuclear life of the original star. Oxygen is produced in large amounts by massive stars before they collapse. So an oxygen-rich remnant suggests the explosion came from a star that had advanced far through its burning stages. These remnants help astronomers understand how such stars enrich galaxies. They also reveal how deeply the explosion dug into the star's interior and how much newly made material escaped. When oxygen glows in the debris, it is not just a chemical marker. It is evidence that the star spent its life transforming lighter nuclei into elements that later became part of planets, rocks, atmospheres, and living chemistry. The glow is therefore both a death signature and a creation signature. It shows matter passing from stellar furnace to galactic inheritance. The brightest debris does not always mark the original explosion center. When looking at a supernova remnant, it might seem natural to assume that the brightest region is where the star exploded. That can be wrong. Brightness depends on density, shock heating, magnetic fields, and the type of material being struck. If the expanding blast hits a dense cloud on one side, that side may shine strongly even though the explosion began elsewhere. The compact remnant, if visible, may sit off-center because of a kick or because the surrounding gas is uneven. To locate the true origin, astronomers compare expansion patterns, motion of knots, and the position of any neutron star or pulsar. They may trace debris backward through time to estimate where the blast began. This detective work matters because the apparent shape can be misleading. A remnant is a projection of a complex three-dimensional event. The brightest patch may simply be where the aftermath is meeting resistance, not where the star died. A supernova remnant can keep expanding for tens of thousands of years. The visible explosion may fade in weeks or months, but the physical aftermath lasts far longer. The debris continues moving outward, first almost freely, then gradually slowing as it sweeps up surrounding gas. Over time, the remnant passes through stages. It begins as fast ejecta, becomes a shock-heated shell, and eventually blends more deeply with the interstellar medium. During this long evolution, it can remain observable in radio, optical, X-ray, or infrared light, depending on temperature and environment. Tens of thousands of years after the original blast, the remnant may still be shaping the gas around it. This long lifetime is one reason supernovae have such influence on galaxies. Their effects do not vanish when the bright point fades from the sky. They continue as motion, heat, turbulence, and chemical mixing. A supernova is brief as a spectacle, but enduring as a physical force. Its aftermath can outlast civilizations. Eventually, old remnants fade into the wider interstellar medium. no remnant remains distinct forever. As the expanding shell slows, cools, and mixes with surrounding gas, its boundaries become harder to define. The material that once belonged to a single star spreads into the larger reservoir between stars. Its elements may join cold clouds, warm gas, dust grains, or turbulent flows. Over long times, the remnant loses its identity, but its influence remains. The energy it deposited helps stir the galaxy. The atoms it released become part of future cycles. This fading is not a failure of significance. It is the way stellar material returns to the cosmic environment. The named object disappears into a broader process. A telescope may no longer isolate the shell, but the galaxy has been changed by it. The remnant's final fate is therefore a kind of dispersal. What was once a dramatic structure becomes part of the ordinary background from which new stars may eventually form. Supernova help regulate how quickly galaxies form new stars. A galaxy needs cold gas to make stars, but that gas is constantly affected by energy from existing stars. Supernova are one of the most important sources of that energy. Their blasts can heat gas, stir turbulence, and push material away from dense regions. This can slow star formation by making clouds harder to collapse. In other settings, compressed shells may encourage collapse along their edges. The overall effect depends on the size of the galaxy, the amount of gas, and how clustered the explosions are. This feedback helps prevent galaxies from turning all their gas into stars too quickly. It also shapes the long-term growth of galactic disks and star-forming regions. Without some regulating process, galaxy evolution would look very different. Supernova act like a thermostat that is powerful but uneven. They do not control every detail, yet they help set the pace at which galaxies turn raw gas into shining stars. Too many explosions can blow gas out of small galaxies. Small galaxies have weaker gravity than large spiral galaxies, so energetic events can affect them more dramatically. If many massive stars explode within a short period, their combined force can drive gas outward and even remove it from the galaxy. This can slow or stop future star formation because the raw material has been heated, dispersed, or expelled. Such outflows also carry heavy elements into the space around galaxies. That means supernova in small systems can enrich not only their own galaxy, but also the surrounding intergalactic environment. This process helps explain why dwarf galaxies can have irregular shapes, patchy star formation, and complex chemical histories. The same explosions that provide new elements can also rob a small galaxy of the fuel needed to make later stars. It is a delicate balance. In a large galaxy, a supernova may stir the local gas. In a small one, many explosions together can change the entire system. Too few explosions would leave galaxies chemically poor and quiet. Although supernova can disrupt gas, galaxies also need them. Without enough stellar explosions, heavy elements would spread less efficiently, and the interstellar medium would remain simpler in composition. Gas clouds would contain fewer ingredients for rocky planets and complex chemistry. They might also lack some of the turbulence and pressure changes that help shape star-forming structures. A galaxy with little recent massive star death could become chemically slower to evolve. Its stars would still shine, but the raw material for later generations would be less enriched. This is why supernova feedback is not simply destructive. It is part of galactic renewal. The right amount of explosive activity stirs, enriches, and cycles matter through different phases. Too much can blow fuel away. Too little can leave the system underdeveloped. Galaxies depend on a balance between calm accumulation and violent return. Supernova provides some of the violence that keeps the chemical story moving forward. Starburst galaxies can host many supernova in a relatively short time. In a starburst galaxy, star formation is happening at an unusually high rate. Massive stars are born in large numbers, and because they live quickly, many of them can explode within a comparatively brief cosmic interval. This makes starburst regions rich in supernova activity, hot gas, and powerful outflows. The combined effect can create galactic winds that carry energy and enriched material far from the star-forming center. These galaxies are important laboratories because they show feedback at high intensity. Instead of one explosion shaping a local cloud, many explosions overlap and merge their effects. The environment becomes turbulent, bright in multiple wavelengths, and chemically active. Astronomers study such systems to understand how galaxies regulate extreme growth. A starburst is not just a galaxy making stars quickly. It is a place where stellar birth and stellar death are closely linked in time. The nursery becomes crowded with future explosions almost as soon as it becomes bright. Distant supernova show how stars died when the universe was younger. Looking far into space means looking back in time. When astronomers discover a supernova in a remote galaxy, the light may have traveled for billions of years before reaching us. That event belongs to an earlier era of cosmic history, when galaxies were younger and their chemical makeup could differ from galaxies nearby today. By studying distant explosions, scientists can compare stellar death across time. They can ask whether certain types were more common in the early universe, how heavy element abundance affected explosions, and how star formation changed from one epoch to another. These observations are difficult because distant events are faint and stretched by cosmic expansion. Yet they are invaluable. They let astronomers watch the life cycle of stars in historical context. A faraway supernova is not merely remote in space. It is ancient in time. Its light carries evidence from a universe that had not yet become the one we now inhabit. Some supernova act as beacons for measuring cosmic history. Because certain stellar explosions are extremely bright, they can be seen across enormous distances. Some are useful as distance markers, while others illuminate the conditions of galaxies in the early universe. Their light helps astronomers trace expansion, chemical enrichment, and the rate at which stars have formed over cosmic time. A supernova can briefly make a faint galaxy easier to study by adding a bright signal to it. It can also reveal dust along the line of sight and help test models of how light travels through an expanding universe. These events are temporary, which makes them urgent. Once discovered, they must be followed quickly before they fade. In that brief window, a dying star becomes a tool for understanding the largest scales of nature. The explosion belongs to one star, but the information it carries can speak about cosmic structure, time, and the changing universe. A flash becomes a marker in history. The absence of nearby supernova can be scientifically meaningful too. Astronomy is not only about what appears, it is also about what does not. If surveys monitor many galaxies and find fewer supernovae of a certain type than expected, that absence can point to missing physics or hidden populations. For example, some massive stars may collapse without bright explosions, or dust may obscure events in active star-forming regions. The lack of recent naked-eye supernova in the Milky Way also tells us something about dust, galactic structure, and probability. Scientists compare expected rates with observed events to test their understanding of stellar populations. Non-detections can rule out models, constrain the behavior of stars, and reveal observational blind spots. This is a subtle but powerful idea. Silence in the data is not empty if you know what should have been heard. A missing supernova can become evidence. It can suggest that stellar death sometimes hides, fails, or happens where our instruments are not yet looking well enough. a hidden supernova in our galaxy could be missed by ordinary eyes. The Milky Way is full of dust, especially along its crowded disk. That dust can block visible light from distant regions, meaning a supernova on the far side of the galaxy might not become an obvious new star in the night sky. It could still be detected in other ways, such as neutrinos, gravitational waves, radio emission, infrared light, or X-rays from the developing remnant. This possibility changes how we think about the next galactic explosion. It might not arrive as a spectacular sight for everyone to see. It could first appear as an alert from particle detectors, followed by a search through wavelengths our eyes cannot perceive. Ordinary vision gives only one limited view of the galaxy. Much of the Milky Way is hidden behind its own material. A star could die within our home galaxy, and the first clear evidence might come not from the sky glowing brighter, but from instruments noticing what human eyes cannot. Dust in the Milky Way can conceal explosions from visible telescopes. Interstellar dust is made of tiny solid grains mixed with gas, and it is especially common in the plane of our galaxy. These grains absorb and scatter visible light, making distant stars and events appear dimmer or completely hidden. This is why astronomers use infrared, radio, and X-ray observations to study regions that optical telescopes struggle to penetrate. For supernova searches, dust creates a major challenge. An explosion could happen behind a dense cloud and be severely muted in visible light, even if it is intrinsically powerful. The effect is not merely inconvenience. It shapes the historical record of what humans have seen in the sky. Some galactic supernova may have occurred without being widely noticed because their light was veiled. Dust is therefore both an obstacle and a clue. It hides events, but its presence also reveals where stars form and where future explosions are likely. The galaxy's own material can conceal its most dramatic moments. Future surveys may find supernova within hours of their first light. The next generation of wide-field sky surveys is designed to scan the sky quickly and repeatedly. This rapid cadence will help astronomers detect sudden changes almost as they begin. Catching a supernova within hours of first light is scientifically priceless because the earliest emission can reveal the size of the star, the presence of nearby material, and possibly the moment when the shock breaks out of the surface. These clues fade quickly as the debris expands. Early detection also allows telescopes around the world and in space to respond while the event is still young. Instead of studying only the bright peak and decline, scientists can capture the opening act. This will improve models of which stars produce which explosions. It may also reveal rare early flashes that were missed in older surveys. The universe has always produced these beginnings, but humans are only now building the tools to notice them almost immediately. Astronomers can sometimes identify a star before it explodes. For nearby galaxies, deep telescope images may already contain the star that later becomes a supernova. After the explosion is discovered, astronomers search archival images of the same location. If they find a source at the exact position, they may be looking at the doomed star before death. This is one of the most direct ways to connect a supernova with its progenitor. It can reveal whether the star was a red supergiant, a blue supergiant, a luminous variable, or part of a more complex system. The method is difficult because the source may be faint, crowded, or obscured by dust. Still, when it works, it is extraordinary. A star once photographed as an ordinary point becomes known later as the object that died. The archive gained new meaning. A picture taken for one purpose becomes a before image of a cosmic catastrophe. This lets scientists compare real stars with the explosions they eventually produce. Archived images may reveal the doomed star after the blast appears. Sometimes the most important observation happens before anyone knows it matters. Astronomical archives contain countless images of galaxies taken years before a particular supernova was discovered. Once the explosion appears, researchers go back through those images and inspect the exact location. They may find a faint star, a cluster, or nothing at all. Each outcome tells them something. A visible progenitor can identify the star's type. A missing progenitor can set limits on how bright or massive it was. Later, after the supernova fades, new images can confirm whether the suspected source has vanished. This process turns archives into time machines. They allow scientists to examine the past of an object that no longer exists in the same form. The method also shows the value of patient sky imaging. Not every discovery is made at the moment of observation. Some discoveries wait in stored data until the universe provides the missing event. Supernova imposters can mimic explosions without fully destroying the star. Some stellar eruptions look surprisingly similar to real supernova at first. They can brighten dramatically and throw material into space, yet the star survives. These events are often linked to very massive unstable stars that undergo violent outbursts. The distinction matters because brightness alone does not prove a star has died. Astronomers study spectra, light curves, later fading, and possible survival of the source to decide what happened. Imposters are fascinating because they reveal how extreme a living star can become. A star may shed huge amounts of mass in a crisis and still continue toward a later true death. These eruptions also complicate supernova surveys, since a sudden brightening in another galaxy may not be a terminal explosion. The name imposter sounds playful, but the physics is serious. It reminds us that the boundary between eruption and destruction can be difficult to see from far away. Some stars rehearse catastrophe before the final act. Eta Carinae survived a giant eruption that looked almost supernova-like. In the 19th century, Eta Carinae became one of the brightest stars in the sky during a tremendous outburst. It released a vast amount of material and formed the striking homunculus nebula around itself. Yet the star did not die. It remains a massive, unstable system today, still watched closely by astronomers. This makes it one of the most famous examples of a supernova imposter-like event. The eruption may have involved intense mass loss, interaction between companion stars, or deep instability in a very massive star. Its survival is what makes the case so gripping. A star produced a display that seemed almost like a terminal explosion, then continued living in a dangerous state. Eta Carinae may still face a dramatic end in the future, but its past already shows that massive stars can behave in ways that stretch simple categories. It is a warning that stellar death may be preceded by violent, confusing episodes. Some massive stars may collapse quietly into black holes. Not all endings announce themselves with a brilliant supernova. For some very massive stars, the core collapse may lead directly to black hole formation with little outward explosion. The star's outer material may fall inward rather than being expelled. From a great distance, such an event could appear as a star fading away or disappearing. Astronomers look for this possibility by monitoring massive stars in nearby galaxies over many years. If a bright star vanishes without a normal supernova, it becomes a candidate for a failed explosion. This idea is important because it could explain why certain expected progenitors are rarely seen exploding. The most massive stars may sometimes die by absence instead of spectacle. That is a deeply strange thought. In a universe famous for brilliant stellar deaths, some of the heaviest stars may end with a kind of gravitational silence. Their final act may be not a flash, but a disappearance. The next Milky Way supernova could transform astronomy overnight. A supernova in our own galaxy would be one of the most important scientific events in modern history. Detectors might catch neutrinos first. Telescopes across Earth and in space would turn toward the region as quickly as possible. Radio arrays, infrared observatories, X-ray satellites, gamma-ray instruments, and gravitational wave detectors would all search for their part of the signal. For the public, it might become a stunning new light in the sky if dust does not hide it. For scientists, it would be a once-in-generations laboratory. They could test models of core collapse, measure the early shock, follow the birth of a remnant, and watch the chemical debris unfold in real time. The event could confirm theories and overturn others within days. Astronomers prepare for it because no one can schedule the universe. The next nearby stellar death may arrive without warning, and when it does, our understanding of stars could change immediately. Supernova remind us that cosmic destruction can become our deepest origin. A stellar explosion is violent, but its meaning is not only loss. Long before Earth existed, generations of stars changed the chemistry of the galaxy. Their deaths scattered elements that later became minerals, oceans, atmospheres, and living bodies. The story is not that a single explosion made everything we are. It is that cosmic history is cumulative. Many stars lived, transformed matter, and returned it to space. That returned material joined clouds that formed later stars and planets. Eventually, one of those planets became a place where atoms could organize into life and awareness. Supernova are part of that chain. They show that the universe can turn collapse into possibility and devastation into raw material. When we study them, we are not only examining distant deaths, we are tracing part of our own ancestry. The most powerful explosions in the sky helped prepare the conditions for eyes, minds, and questions beneath that same sky. And so, our journey through supernova comes to a close. Tonight, we followed stars to the very edge of their lives and saw how their final moments can reshape the universe around them. We watched massive cores collapse under gravity. We saw white dwarfs flare into sudden brilliance. We traced shockwaves through gas and dust and followed the strange remnants left behind, from spinning pulsars to silent black holes. We also saw that these explosions are not only endings, they are part of a much larger cycle. Supernova scatter elements into space. They stir galaxies. They leave glowing clouds that can last for thousands of years. And in the long story of the cosmos, they help prepare the ingredients for planets, oceans, bones, and breath. There is something deeply calming in that thought. Even the most powerful events in nature are woven into a larger order. A star can fall apart and still give something back. A flash of destruction can become part of the future world. The universe wastes nothing. It gathers, transforms, releases, and begins again. So now, let those thoughts soften. Imagine the sky above you growing darker and wider. Somewhere far beyond sight, an old remnant is cooling. Its light is fading. Its dust is drifting slowly into the dark between the stars. There is nothing you need to solve now. Nothing you need to hold. Just let your shoulders drop. Let your breathing find its own easy rhythm. Let the day move farther away until it feels small and distant. If you enjoyed this curious journey, you're welcome to like, subscribe, or leave a thought below. It helps others find their way here too. And if you're still awake, another sleepy science journey should be waiting on screen for you now. But for now, let your eyes grow heavy and let the universe feel calm around you. Sleep well and good night.